All right, so we'll explain today, as we already did a little bit, how refrigerants affect the ozone layer, identify CFC, HCFC, HFC, and blended refrigerants, identify refrigerants most often used in the HVACR trade by color and code. This book's already old because guess what, color and code, there is no more color. And describe refrigerant properties. Summarize common applications of various refrigerants, explain properties of inorganic refrigerants, and identify the properties and properties of lubricants used with refrigerants. So the ozone layer, all right, we've got that. Everybody knows what the ozone layer does, I hope. Basically, it's keeping out the bad rays from attacking us, the UV radiation. UV radiation is bad because it does create cancer, all that sort of stuff. So we've got this nice protective bubble of O3, which is ozone, protects our rays from hitting the earth. We did develop a hole. With that hole, we've got issues. We've got these rays coming in and having some issues. The reason we have these holes, it's because of refrigerant, or at least they say. I'm not a scientist. Anyways, the ozone is getting eaten up by the chlorine that's in the refrigerants. The chlorine destroys the ozone, and we start to develop these holes. Okay. Montreal Protocol, they wound up deciding that R22, R12, all the bad stuff out there no longer is going to be used in air conditioning systems, refrigeration systems. So therefore, we're going to protect the environment, we're going to protect the planet. So we've got the Clean Air Act, all right. It's going to tell you the guidelines, restrictions, and penalties for releasing refrigerants into the atmosphere. Fines up to $37,500 per day for failure to comply. So basically, don't be one of those guys just releasing refrigerants into the air, all right. You forgot your recovery tank at home. You're working on a system, you're like, nobody's watching, I'm just going to cut the line and release it. Not only is it bad for the environment, you'll also get oil all over the place, because remember, there's oil that's inside our refrigeration systems. And secondly, if somebody sees you do it, they're going to call the EPA or anybody else, and they're going to fine you. And I think there's like a $10,000 reward. So if somebody does piss you off and you don't like the technician or whatever, you can just say, he was releasing refrigerant into the environment, and call it a day, and hopefully you'll be rewarded handsomely. So the results of the Clean Air Act: training and certification required to handle refrigerants. Yes, EPA licensing. We need to be EPA certified in order to handle refrigerants. So that doesn't mean we can, that's, hey, my boss called me and he needs me to bring this jug over and I need to be EPA certified. No. What that means is I can't hook up my gauges to a system without having that card. If I don't have that card, I can be fined, all right? Or your boss can be fined, or anybody else. So anytime you're hooking up gauges to a system, non-classroom setting, classroom setting is completely different, but you want to make sure that you're EPA certified. So if you're looking for a job, you're saying, hey, I want to be getting to the HVAC field, that sort of thing, you need to make sure that you're EPA certified. There's 4 different levels for the EPA certification. There's the core, then there's level 1, 2, and 3. Core is just going to be your basic stuff that you can take. You can just Montreal Protocol stuff, whatever else is on there, I can't really recall. But then you have your 3 other tiers. Level 1 was systems up to 5 pounds. Those are usually like water coolers, small little systems that you would be able to work on. You don't have a lot of charge with them. Level 2 is going to be systems that are going to be like residential size. I don't remember what the range is, 10, 25 pounds, something like that. And then your level 3 is going to be your commercial, industrial, all the big stuff. You can hook up your gauges to just about anything at that point. And if you hold all 3 levels plus the core, you actually get an EPA universal certification, so you're going to work on any piece of equipment. If you pass the core and you fail level 2 and 3, Well, guess what? You still pass and you get just level 1. You always have to pass core along with a level. If you do fail it, I think you can retake levels 2 and 3 if you fail those the first time. So once you take the test, the place wherever you're taking it is going to explain all that stuff. You can't take it online, or at least I don't know if you still can. The reason being is they want the test to be observed by an individual, so there has to be a proxy there, making sure you're not cheating or anything like that. When I took mine, I got thrown into a closet and I could look up on my phone if I really wanted to. So not saying that's the case, but it may be for you guys. But not a super hard test, but you do have to know your information, things like that. Depending on who you go through, they may give you a little study guide to use to prepare you for that exam. All right. Let's see. The whole purpose of having the EPA is we're going to prevent significant releases of refrigerant into the atmosphere. What does that mean? Can I not release refrigerant whatsoever? No. When we're handling refrigerant, we're going to purge our lines, we're going to bleed our lines, that sort of thing. And I'm talking about our hoses, our gauges. That's acceptable. All right. We need to get the old refrigerant out of our lines because I just worked on a 410A system, or our hoses, I should say. We're not going to hook up our 410A hoses filled up, with refrigerant into an R22 system. So I have to release all that gas out so that I can work on a 22 system. That's acceptable. Going up to a unit, cutting it, releasing all that refrigerant is not. All right. There are exceptions that allow technicians to do their job. Like I said, we're going to release tidbits of refrigerant up into the atmosphere. It's just part of doing it. There's just no other way. But we're trying to capture as much of it as we can. The other thing too is when you're working on refrigerants, your hoses have to have some type of safety device on there to hold the refrigerant inside the line. Back in the day, it would just be the hose. As soon as you undid the hose, all the refrigerant would just leak out. So now there's one-way valves on there, so the refrigerant stays inside your hoses, or there's little ball valves. I personally like the little ball valves, easier. I can open, close, do a little bit more as opposed to just the one-way type. All right, methods of measuring the impact. Somebody came up with this and they basically rated it. All right, ODP compares refrigerant to R11. We don't use R11, but that we use one of the refrigerants back in the day, and so we get this value of scale of 0 to 1. Okay. We also have the GWP, the global warming potential. That's a little bit more of what people understand, especially with the new types of refrigerant. They're not going to hurt the environment by creating a greenhouse gas that's going to trap that heat inside of our planet. So here's our ODP, ozone depletion potential. Basically what we're saying is the refrigerants are going to destroy the ozone because they have chlorine in them. R11, R12, we don't use those because they are really bad for the ozone. R22, slightly better, actually much better, but still it does deplete the ozone. 410A doesn't, but it still does have a high GWP. So we're eventually going to switch over to, like I said, an R32 or Carrier's proprietary blend. Oh, they do have the gray tank on here, so that's cool. CFC refrigerants were the first halogen-based refrigerants. They contain chlorine, fluorine, and carbon. The chlorine atoms break apart the ozone. Major cause of ozone depletion. All right, we've already talked about all this. They're no longer made, but still found in pre-1995 equipment. R12, that was actually really popular with automotive vehicles. Everybody's car had R12 in it. You can still find R12 a little bit here and there, but all new vehicles no longer have R12, right? So then, after R12 became HCFC refrigerants, composed of hydrogen, chlorine, fluorine, and carbon. So we still have a little bit of chlorine in there. Partially halogenated. They have less of an impact on the ozone layer than fully halogenated CFCs, high GWP, and then EPA requires phase out by 2030. So EPA by 2030 says no more R22. I think we'll honestly run out of R22 by that point, but you know, we'll see. All right, HFC refrigerants composed of hydrogen, fluorine, and carbon, partially halogenated, no chlorine atoms, so they're not going to destroy the ozone layer. They do have an ODP of 0, but a high GWP. All right, so they have a high global warming potential. They're going to create greenhouse gases, and they're going to be replaced by lower GWP alternatives. So we have a refrigerant classifications, all right, CFC, HCFC, and HFC, and these are just the atoms of each, all right. Halogens replace hydrogen, hydrogen atom meets HCFC and only partially halogenated, so basically these are just the building blocks of the refrigerants. We do have different refrigerant blends, okay. Oh, let me go back. So a refrigerant blend is a mixture of 2 or more refrigerants, all right? We have azeotropes, zeotropes, and near azeotropes, all right? The blends are still classified by their component, refrigerant, CFC, HC, so forth. Never attempt to make a zeotropic or azeotropic blend. So what does that mean, all right? So when we get these blended refrigerants, I'm gonna have 3 different types of refrigerants in there mixed together to make one. All right, 410A is actually an example of that. And so why do we have to know this? Well, the reason being is if I were to go and charge a system with R22, it's its own proprietary blend, all right, or not proprietary, but its own single blend. I can charge that system as a vapor, okay? I'm going to release vapor refrigerant into the low side, and we're going to charge up the system. If I were to do that with 410A, because I have 3 different types of refrigerants, what's going to end up happening is I'm going to have one refrigerant that's going to boil off faster than another, and so I may end up getting a higher concentration of the first refrigerant, a little bit less of the second, and nothing of the third. And so now all of a sudden my system isn't going to operate like it's supposed to because I have the incorrect mix of gases going into my system. So I may have basically created my own blend of refrigerant at this point. So what we do is we're actually going to take our tank and we're going to invert it. So it's going to be upside down. And as we start to release the refrigerant into our system, we're going to start releasing it we're going to start charging it as a liquid. That liquid's going to travel up through our gauges, and we're going to throttle our gauges so that way the refrigerant coming up to our gauges is going to be a liquid, and as it exits our gauges, it's going to flash, and then it's going to go into the system. So we're minimizing the amount of fractionation occurring, all right? So we're sort of acting as a metering device with our gauges, so that way we can really let all that refrigerant get into our system properly. All right, azeotropic refrigerant blends respond to changes in pressure and temperature like a single refrigerant. All right, so that means that they're going to act similar to like a R22, okay? Even though they are a blend, they're still going to act as like a single refrigerant. So with these, you're going to be able to charge them possibly as a vapor. The problem is they still may fractionate, so I'm not completely sure about 500 and 507A because I've never had to use them. If you're unsure, you could always charge it as a liquid and just make sure that you flash them before it enters into the system. All right, they maintain consistent properties. Most contain a phased-out refrigerant, often called azeotropes. We also have a Azeotropic refrigerant blend. Well, there's our guy, 407C. Each component refrigerant responds individually. Range of boiling and condensing points. Fractionation of individual refrigerants. Creates a temperature glide. Can change phase and temperatures simultaneously. So we've got a lot of different things going on because we've got the different gases inside there affecting different things that are happening inside of our system. So we've got the fractionation, I should say. The refrigerants are separating, and we're not getting the proper benefits of the refrigerant that we're really looking for. So then we have the newer refrigerant types, the hydrofluoroolefins. They have a 0 ODP and a low GWP value. One of these is HFO 1234YF, and they're being used in the automotive side for the EC systems. All right. We also have 1234ZE, used in residential, light commercial, heat pumps, commercial refrigeration, and various other applications. And that's one of those refrigerants yet again. It may be coming out. One of the manufacturers may jump on it and say, you know what, hey, we're going to be using 1234ZE in our products. All right. We're already using 1234YF in automotive applications. So that's another possibility. You know, maybe, I don't know, a Ream or somebody or Rude decides that, hey, we're going to jump on this and this is going to be our refrigerant type. All right. We also have hydrocarbons. They have a 0 ODP and a low GWP value, but they're highly flammable. All right. That's of concern to me. Okay. Why? Why is that a concern? Well, we're working on equipment. Okay. When we're working on pieces of equipment, if refrigerant were to leak out, normal refrigerant is going to displace oxygen. So if there's a refrigerant leak, get out of there. We don't want to be in there. We want to make sure that there's ample oxygen in there. So if you're in a confined space and there's a refrigerant leak, get out. All right, we're not going to mess around with it. Let it air out, let it leak out, you know, whatever the case may be. There's just nothing you can do at that point. You don't want to kill yourself over something. Now, what if we have a leak and now our refrigerant is flammable? That's a huge topic of discussion. That's why we haven't really seen some of these flammable refrigerants coming over here. Overseas, they have a lot of heat pumps. They have a lot of ductless systems. So they don't have an open flame like we do with our furnaces, all right? They don't have the ductwork like we do. And so now all of a sudden, if we have our refrigerant system, you know, we've got our evaporator, it's sitting over the top of our furnace. And usually refrigerant is heavier than air, okay? It starts to fall down, we get a leak, it starts to fall down into our furnace, and all of a sudden it comes in contact with our flame. What's going to end up happening? Are we going to get an explosion? You know what? I don't know. I don't know enough about the flammable refrigerants, but that is why they still haven't come over here. It's possible. It's definitely going to be coming, but what's going to happen in the meantime? It may be quite a bit of time before this does happen. The other thing too is the equipment that we use to service equipment, to service the refrigeration equipment. It's designed for a specific refrigerant. Okay, if all of a sudden I put a flammable refrigerant through it, my equipment may combust. It may explode because it's going to ignite that flammable equipment. So what that means is now we're going to have to buy specialized equipment like vacuum pumps or recovery machines or anything else that's sort of electrical to mitigate the risk of the dangers from that flammable refrigerant. So it's a whole other world right now if we do get into those. There are different refrigerants out there that do have the potential for explosion. So one of those is, you know, R600A, R290, which is propane, and then we've got a R441A, which is a blend. So keep that in mind. So HFOs are mildly flammable. Studies are helping develop standards for safe usage. Yeah, basically they're like it cools and makes the things run, but they're potentially dangerous, especially here in the States with the furnaces and everything else and the flammable products that we have. And then we have the water heater as well. So, all right. We also have a classification. There's different classifications for different refrigerants. Low toxicity, high flammability. All right. Only some HCs are approved by significant new alternative policy. So not every flammable refrigerant is going to be used. All right. We want something that's going to be low toxic, hopefully low flammability, but it just all depends. All right. So how do we identify refrigerants? The first digit indicates refrigerant series. Okay. Significance of remaining digits depends on refrigerant's classification. So if we're talking about a R410, all right, it's a refrigerant blend. That's a zeotrope. If we start getting into the 500 series, now we got refrigerant blends, which are azeotropes. We also have, the 1, 2, 3, 4, which are ethane based, and then we have the 200 series, which are propane. So if you come across a 200 series, you know that it's flammable because of the propane that's inside there. We've got organics, inorganics, and so forth. But each one has its own designation, so you know what the constraints are of each refrigerant. So the refrigerant numbering system, all right, third number from the right indicates the series. Next two numbers are assigned sequentially to or denote number of carbon and hydrogen atoms. Great. I think some chemists thought that this was really interesting. I don't know if you guys are chemists or not or interested, but I never really cared about how many carbon atoms or hydrogen atoms were in this, but it's explaining how we came up with R134. All right, and then the A indicates unbalanced isomer. I think the most important thing for you guys just to understand the different series, the 100, 200, 400, 500, 600, just being aware of what refrigerants do what. So the refrigerant cylinder code doesn't really exist anymore, okay? It used to. It was supposed to help prevent accidental mixing. Well, it didn't. So now we're going to just have all race cylinders. All right, so you're always going to have to read the label and never put used refrigerant into a cylinder. All right, so that's also going to limit the amount of accidental refrigerant charging in a system. So refrigerant cylinder color code. Refrigerant cylinder color code chart. All right. It was a cool little chart back in the day, but like look at R503 and 507A. I mean, how do you really distinguish between the two? All right, one's blue-green and the other one's blue-green. To me, they almost look identical. So that's why they got away with that. Toxicity and flammability. Class A refrigerants not known to be toxic at or below 400 parts per million. All right, well, that's good. Class B refrigerants known to be toxic at or below 400 parts per million. All right, so we've got different levels of toxicity based on the refrigerant type. Okay, not only do we have to worry about it potentially hurting us by poisoning us, we also have to worry about it potentially exploding in our faces. So we have different ratings. We have flammability ratings. We got 1, 2, 3. Oh, of course, and we have a 2L. So low flammability and slow burn velocity. So we have the different levels, A1, B1, and so forth. So different designations for different types of refrigerants. And so here are all the different refrigerants. So if we go back to our chart and we look and we get, okay, I get a refrigerant, you know, it's got a sort of low toxicity. All right, so my toxicity for the most part is good, but then I get into like a 123 or a 717, I have to worry about it potentially being harmful. All right, if I go back and I look at the flammability, all right, B3, all right, any flammable threes are 290 looks like it's pretty flammable. So the good thing is it's non-toxic, so it'll be safe. But just understand, you know, there may be certain issues. So if we're brazing, refrigerant leaks out, we may have some issues. Okay. Pressure temperature curve shows the relationship between refrigerants, temperature, and pressure. All right, it's used to determine if a unit is operating at correct temperature or pressure. So PT chart, great stuff to utilize. You guys got to be using it all the time. You want to make sure that the system's operating, you know, properly, or you know, making sure that the refrigerant is operating based on the pressure temperature chart. Okay, if I read a certain temperature, I should have a certain pressure. If I don't, well then I may have some superheat, I may have some subcooling going on, or I may have something else completely going on with the system. So we have a pressure temperature curve right here. Basically, you know, if we're going to take R22, and we're going to take R22 and we're going to go down to about 70 degrees, I know my pressure is going to be 120. All right, remember earlier I was talking about how do I know the difference between a 410A system and an R22 system? Well, I go to my PT chart, okay? I'm going to look at my pressure. Let's just say my pressure is 120. I know what my temperature is. Well, then I know it's R22. At 70, let's say at 70 degrees, but now my pressure drops. Well, guess what? If I'm at close to 85 or so, I know I'm an R500. Working on different pieces of equipment, like for example, you're working on a residential air conditioning unit, generally you're only going to be a few different types of refrigerants. You don't have to worry about that so much. But if you start working on commercial applications or other things, then you'll notice a little bit more of a difference as far as refrigerants. So you don't have to worry about so much of the different refrigerants on the residential side. You'll have to know more of them for the commercial side, but regardless, you'll still have to know the PT chart and how to get your measurements. So what I've got is there's actually a app that I use. Let's see if I can pull that up really quick just to get you guys this. So if you actually go to the Apple Store or Google Play, whatever the case may be, whatever phone app you have, you download this guy, Dan Foss's Refrigerant Tools. Real nice, real easy to use. It's free. You can basically clock in the type of refrigerant. You slide up this dial, the gauge, whatever the case may be, and it's going to tell you exactly what your PT corresponding numbers are. So this is what I use if I need to. I'm sort of spoiled. My gauges tell me exactly what my PT, my pressure temperature curve is, or what's happening. It tells me my saturation point and all that stuff. And ideally, that's what we're really talking about too. Is why do we need to know this? We need to know what our saturation point is, and this is going to tell us. And then from there, I'll be able to know what my superheat and subcooling are. So PT charts, cool. They've got one here for you. So this is for R134A. So the really cool thing I like about refrigerants is that at atmospheric pressure, okay? So we're talking about at almost zero. Our refrigerant boils at -15. So as soon as you open up the lines and you release this refrigerant to the atmosphere, it's vaporizing. It's gone. But it's going to stay into a liquid state until it absorbs enough heat for it to turn into a vapor. So that being said, we're always going to wear eye protection. around equipment. The reason being, you may get liquid refrigerant that may hit you, and we don't want that getting into our eye. Because if we get, let's just say atmospheric, what do you call it, 134A, and that comes shooting out at -15, well, our eye just hit -15 degrees, and that's going to basically destroy our eye. All right, so make sure you wear eye protection. I was working on a piece of equipment one day. It was a little refrigerant system. I think it was operating off of like a R134A. Actually, I think it was R134A, and it had leaks. And so I'm working on the king valves, opening it up, just trying to diagnose the system, figure things out. As I'm opening the king valve, I'm up on a ladder. All of a sudden, this little stream just comes out of the top of the king valve, and I'm like, what's going on? I was just shocked. It was liquid refrigerant just pouring out of the system. System's running and this thing's just pouring out. It almost hit me in the eye. I mean, luckily I was wearing eye protection, but it was a good 5-6 inches away, and I'm like, you got to be kidding me. Never seen it. Nobody I've ever talked to has ever seen anything like it, but you just never know. All right. If you're releasing refrigerant out of your line, out of your hoses, and all of a sudden, it hits something, or your line bumps and releases some refrigerant, it may hit you. So we want to make sure that we always wear eye protection. The other thing too is wear a good pair of nitrile gloves. Nitrile gloves, they're going to take the brunt of the cooling away from your skin for a brief second, and you're going to still have dexterity in your hands. So if I'm disconnecting hoses or I'm doing something, that refrigerant's going to hit your hand, but you're not going to feel that burning sensation, all right? And you're still going to be able to work and move your hands. If I had a pair of leather gloves or anything like that, as soon as that -15 degree refrigerant hits it, that glove is just going to turn into a rock, and it's not going to be able to move. So just a good old pair of nitrile gloves is going to do that. All right, so back to the PT chart. All right, values are for saturated refrigerant conditions. All right, so we're at that point where if we start to remove heat or apply heat, our refrigerant is going to change state. All right, it's going to go from a vapor or to a liquid. So we're right at that little middle point. Okay, these things are available as cards, folded papers, and electronically. Back in the day, the supply houses used to love giving out these things. Everybody had one in their wallet, that sort of thing, but not anymore. Put it on your phone, you're done. All right, so then we also have a pressure enthalpy table, and it lists the actual operating temperatures and pressures. All right, so it shows a volume of 1 pound of vapor and the density of liquid refrigerant at a given temperature. So enthalpy is really the heat content. All right, so we want to know what the heat content is, because that's going to affect our charge. All right, vapor heat content minus liquid heat content equals latent heat. So here we are, we're talking about latent heat. We're talking about that that heat that it takes to melt an ice cube. We start applying heat to our cup of ice, water. We're seeing the ice melt, but our temperature isn't changing. Why? Because we've got latent heat. We've got heat that we can't see that's being used to turn the shape of the ice into water. Okay, so we have a pressure enthalpy table example. All right, so basically what we're looking at here, so at a temperature, and this is R134A, at a temperature of 0 degrees, we're going to have a pressure of 21. So we know that, that's exactly what we're talking about, -15. Sorry here. Oh, it's PSI atmospheric. I'm sorry, that's why it's throwing me off a little bit. All right, so back to the temperature, 0 degrees Fahrenheit. We have a pressure of 21.17. We have a volume of 2.16. So this is how much space that refrigerant is going to take up. All right. Liquid density, this is how much space that liquid line is going to take up, or the liquid is going to take up. All right, so we can then see how much BTUs we get per pound out of this. So as liquid, we get 12.21, as opposed to a vapor, we have 103.16. So what does that mean? That means that we can actually remove more heat from a space with the refrigerant being a vapor than we could if it were in a liquid form. All right, so we're going to have a larger line. All right, so we've got our vapor line in our system. All right, they're either usually like a 3/4 or 7/8 inch size. The reason being is because I have so much more room to fit all the vapor inside there to remove all the heat inside the house. All right, so we're going to let the vapor do all the work for us, and we'll just let the liquid reject the heat. Okay. So it's a visual graph of thermodynamic properties. Same information contained in the pressure-enthalpy table, used to help to understand how each component functions in a refrigeration cycle. And it shows the temperature glide for azeotropic blends. So we've got this chart, okay? So this is something you guys may see, may not see, you know, whatever the case may be. Usually, most of the time, we're trying to be somewhere in this range, all right? It's hard to say on this particular one because the true enthalpy diagrams, there's lines going everywhere, all over the place. So what we're I'm trying to really explain this one, guys, and they're not giving me the information that I want out of it. Let's see if the next slide does. Ah, there it is. Okay. So over here, we've got our pressure, okay, in PSI atmospheric. So we want to follow the lines to make our connection points, okay? We also have our enthalpy down at the bottom. We follow those lines to make the points. This is all for R134A, which has a designation as fluorine. That was something I never talked to you guys about too, is if somebody says, hey, you know, I need some, what the heck is it? No, I'm blinking out here. R22 has there's a proprietary name to it, Freon. You know, oh, I need some Freon, I need some Freon. It's like calling Kleenex, you know, by its brand name. Freon is just a brand name for R22. There's different manufacturers for it, but just understand that, you know, if somebody says, hey, I need some Freon, it's just R22. All right, so where are we at here? All right, so we've got this enthalpy chart, and so we try to follow the pressures and the temperatures to meet at a certain point based on our conditions. Without going too much into detail, this chart is really telling you how the refrigerant is going to act at a certain temperature based on the conditions that are happening inside the room. And it's going to tell you how much BTUs I'm able to remove from that space. So every chart is going to be different because every refrigerant is going to act differently. So if I were to compare this chart, say, to an R22 or even a 410A, they're all going to have these different temperature glides, which are going to affect how the refrigerant is going to act and how much cooling we're really going to get out of a space. All right, it's the simplest, easiest way for me to explain it. Coefficient of performance, it's the ratio of refrigeration effect to heat of compression. All right, so higher coefficient means better efficiency. Used to determine which refrigerant will be most effective in a specific system. Okay, so basically what we're doing is we're trying to figure out, as we start moving this refrigerant around, which one's going to be the best based on the different applications that we have. Okay. In going back on that, different refrigerants act differently depending on different conditions, and so one refrigerant may not work perfectly for another application. So that's why there's so many different refrigerants out there for different applications. I can use 410A to cool off a home, but it's designed for the temperatures that we want to maintain in our home. Let's just say it's about 70, 75 degrees. I'm not going to use 410A to cool a flower cooler. It just doesn't have the curve, the blend to make it work properly, and so the BTU output at the design temperature, let's just say 40 degrees, isn't that great, so I'm not removing as much heat out of the space as I could, and so they're going to use another refrigerant that's going to remove it at a better temperature. And so then we use that COP to figure that out. All right, so we got the different refrigerant applications. It's based on the pressure, temperature, and heat properties of the refrigerant. So, all right, items to consider: boiling point, latent heat, operating temperatures, operating pressures, equipment size. So this is all what the engineers are going to be doing to figure out what's going to work best for that piece of equipment. All right, there's some certain times that there's equipment that you're going to run into that's capable of running 2, 3, 4 different types of refrigerants, and based on the application, you can select what refrigerant is going to work best. But we have to make sure that when we do that, we put in the right metering valve, because that metering valve is going to operate differently on one refrigerant than if I were another one. So CFCs, they were phased out in 1996, may still be purchased from a stockpile by EPA certified technicians. So we've got to make sure that we are EPA certified to buy refrigerants. Not only to buy refrigerants, but to hook up our gauges and that sort of thing. If you go to any shop, any supply house, first thing they're going to ask you for is your EPA card. If you don't even have an EPA card, you can just turn around and walk away, because they're not going to help you. If you guys are students, that's a different story. You can walk in there, you can say, hey, I'm a student, I'm looking to see if you guys have tools or whatever. They'd be probably more than happy to help you out in that regard. But if you're trying to buy refrigerant, they absolutely won't do anything. If you're trying to buy a furnace, a lot of places won't even sell you furnaces, even though it's not related, but it's in the same industry, you're still not going to be able to get anything. All right, back to the CFCs. Phase out to be completed in 2020 in the US, illegal in new equipment since 2010. So as of 2010, no more production. All right, so even trying to find a compressor, all right, trying to find compressors for R22, you want to replace a compressor in a system, it died, yeah, no, good luck. It's not going to happen. You may find like an old one sitting around, but why take that chance? We know that the system's pretty old already, so let's just not do that. It may just be more beneficial for the customer just to replace that system. If you need to top them off a little bit, that's fine. Some industrial equipment out there, it holds hundreds of pounds of refrigerant. Yeah, good luck in trying to convince them to replace their system. That's not going to happen, so at that point you are going to have to top it off. Also, part of the EPA test is knowing what the leak rates are, the acceptable leak rates. Each equipment may leak, may not leak, and there's certain leak rates that are acceptable. I can't recall off the top of my head, but I think I want to say like 40 pounds, a 40-pound leak rate. So if your residential system leaks less than 40 pounds per year, well then, you're good to go. You don't have to replace it. If it leaks more, then you have to replace it. 40 pounds does seem excessive, but like I said, I can't recall off the top of my head what that leak rate is. But that's how they determine if you should repair it or you should replace it. All right, so we've got commonly new refrigerants. 134A, 407C, it's the retrofit for R22 equipment. The other thing too I don't like about 407C is it's another jug that I have to carry on my truck. You already see how many jugs are out there floating around. Do I really want to throw another jug into my van, you know, if I'm going to have 3-4 jugs already in there, do I need a fifth, a sixth, a seventh? My van's going to be an entire collection of different refrigerants. You know, it's almost like an ice cream truck at this point. You know, come and get your flavor. We got 448, 454, 410A, new air conditioning, 508B, low temperature equipment, and then the automotive 1234 YF. We also have ammonia. All right, ammonia is used in different applications. It's used mostly in the industrial sector. It's a chemical compound of nitrogen and hydrogen, and it has a low boiling point. All right, so it's got temperatures well below zero without pressures below atmospheric. So it's going to be used in a lot of like freezer applications, making sure that things get really cold, stay cold, that sort of thing. It's got a large refrigerating effect with smaller machinery. So it's great. The problem is it's extremely flammable, and it has strong effects on our respiratory system. So you really have to be specialized to even work on ammonia equipment. They're just not going to let anybody do that. I think there's only like one outfit in the Chicagoland area, maybe two, that do work on ammonia systems. If there is an ammonia leak, you know, it's like one of those things that you see in the movies. The entire hazmat team's there evacuating people and that sort of thing, because it is a very dangerous refrigerant. So keep that in mind, but it does do well as far as handling sub-zero temperatures. So when you're working with ammonia, wear a tight-fitting respirator. Stand to one side when operating the ammonia valve because it is so damn cold. Use sulfur candle or spray vapor to detect leaks, and follow all training and safety protocols. You may even be wearing like a ammonia detector, something that'll trigger. There may be even alarms if there are leaks of ammonia or even other refrigerants for that matter. So if you walked into a store or an industrial sector, and let's just say their condenser is in a small little room for whatever case, and you know it's leaking, well, you're not going to smell it because most refrigerants are odorless. You walk into the space, you may suffocate because the refrigerant has displaced the air and you die. So in that case, if you walk into these smaller rooms, it's nice to have like a little personal monitor that's going to detect the refrigerant. Sometimes they even have alarms in the different spaces to identify when the refrigerant leaks, which is also nice. Right? We have cryogenic fluids used in processing plants to rapidly freeze food. All right, rapid freezing reduces ice crystals, results in less damage to food during freezing. It must be kept in insulated vacuum containers and expandable. So this is just basically the process, or just a little diagram of what ends up happening here. Basically, it just shoots a bunch of cold stuff at the product, freezes it, and we're good to go. So when handling cryogenic fluids, never allow fluid to touch the skin. All right, so like one of them would be liquid nitrogen. All right, everybody's heard of liquid nitrogen. Maybe you've even seen demonstrations where somebody takes a rose, dips it in, pulls it out, and now all of a sudden they're able to crack or smash the rose into millions of pieces because it's basically turned the rose into a fragile ice block. All right. Protect your entire body with suitable clothing, helmets, and gloves. All right. Yet again, these fluids are extremely cold, and so any of that stuff getting in touch with your skin, your eyes, is going to burn it or destroy it. So we're talking about what's the term that I'm looking for? Frost. Either way, it's going to freeze your stuff, and you don't want that. All right, so here's our confined space with the expandable refrigerants. All right, releases an expandable refrigerant to atmosphere after one use. Okay, so refrigerant is not collected for reuse, and it's also called open cycle or chemical refrigeration system. So basically, they're just expelling the refrigerant into the atmosphere and calling it a day. All right, one of those, liquid nitrogen. Okay, Once we use liquid nitrogen, that's it, we're done. We can't recover it, so we don't have to worry about it. The nice thing is most of our atmosphere is made of nitrogen. We're good to go. So then there's also refrigeration lubricants. We want to make sure that we put in the right lubricant into our system, or make sure that that lubricant is in there. It helps move or keep the compressor lubricated. Certain refrigerants respond better to different lubricants than others. Okay, the lubricant helps the moving parts of the compressor or anything else that's in the system that may be moving. Usually it's only the compressor, and the lubricant must be able to travel freely through all parts of the system. All right, that lubricant and the oil, they sort of get attached, they start moving throughout the system, so the inside of your line set gets covered everywhere with that lubricant. Characteristics of refrigeration lubricants: it's got low wax content, high thermal and chemical stability, low pour point, low viscosity. Basically, it means it's just going to naturally flow. It doesn't take a lot of heat to get it going, so it's going to keep everything nice and lubricated. All right, wax content precipitates out of the lubricant at low temperature, can plug control orifices and clog a system. All right, so we want to make sure that depending on the application that we're using, we're putting in the right oil along with the right refrigerant. The reason being is I don't want this wax separation to occur and potentially clog up our system. All right, we have a flock test, determines how easily wax separates. Flock point is the highest temperature at which precipitate appears. All right, so we want to make sure that our lubricant stays together and it doesn't start to separate. All right, if we apply heat to a lubricant, it can break apart, fall apart. So we've got the thermal stability for it, and we also have chemical stability. All right, make sure that nothing happens to it, when it reacts with refrigerants or substances. All right, and then of course the flash point. So if things get too hot, we may start to create vapors from that lubricant. And of course, viscosity. All right, the most important part, I think, in my opinion, measure of liquid's resistance to flow. All right, so we're going to have different viscosities based on different applications. Just so like our cars require different viscosities based on the different conditions we're driving in. All right, so there's two different viscosities in oil, our car oil. Let's just say, for example, a 0 W30. The 0 is going to take care of colder conditions, whereas the 30 is going to take care of the higher temperatures and conditions. All right, outside. All right, so we have the higher temperature reduces viscosity, lower temperature increases viscosity. And of course, there is the pour point, which is the lowest temperature at which a lubricant will flow. So if our lubricant's going to flow at 70 degrees, cool, but it may not flow at 32. All right, that may be a problem, especially with refrigerants, because we are going to be going potentially below freezing with our refrigerants, depending on the application. And so we want to make sure that our lubricant is going to work well with the refrigerant and the application. So we've got a couple of different types of oils. We're usually going to have either mineral oil or polyol ester oil, POE. What ends up happening is mineral oil, you're going to find that with R22 systems, and then you're going to have the POE or the synthetic, and you're going to find that more in the 410A systems. And then you have the alkyl benzene, which you find in different blends, and then the polyalkylene glycol. I've never had to deal with or work with alkyl benzene or the poly. It's usually either the mineral or the polyol ester. So they don't really mix too well. You don't want to just pour a bunch of POE oil into MO and just call it a day. You want to really remove the mineral oil if you can from the system as best you can. With that being said, if we're working on an R22 system, and what will end up happening is we've got that light coating on the sidewalls of our copper tubing. We've pulled out the condenser, we've pulled out the evaporator. Now, how do we get this mineral oil out of the tubes? According to most manufacturers, you don't have to do anything with it. The little bit of mixing with the mineral oil and the polyester oil isn't going to hurt the system at all. There's some companies that used to, or they still do, will use a flush. And basically what the flush does is it actually sends a chemical agent which scrubs the sidewalls of the copper tubing, and it cleans all the gunk out of the system. The problem with it is if it's not done properly, well then that flush stays in the tubing. And you seal up the unit, and all of a sudden the flush is inside there, and it gets run around, and it actually destroys your system because it's not supposed to be in there. So a lot of these new manufacturers, or most manufacturers now, are saying, you know what, don't worry about the flush because there's potential for more damage than good. And so whatever mineral oil is on the sides is perfectly fine. But we're not going to just take mineral oil and POE oil and just dump them together and mix them. So trying to keep those two things separate. So we've got compatible refrigerants and lubricants depending on the type of oil that we're working. So let's just see if they, so POE oil, 410A, if we go back to 22, MO, mineral oil. Like I said, a little bit of POE and MOE is okay, but I mean, we're talking about what's ever left on the sidewalls of the system. We're not going to just pour jugs in and call it a day. If we looked at 407C, hey, look at that, POE. They say it's a drop-in replacement for R22. Nope, it's not. I have to put, my synthetic oil in there first before my system is going to operate. So, it also says that in like the fine print when you do try to put in 407C. So I just say, to heck with it. You know what? I'm just going to put you in a brand new system. All right, handling refrigerant lubricants. Keep lubricants in a sealed container. Transfer lubricants in chemically clean containers and lines. Do not expose to air and moisture. And buy small sealed containers. Reseal container after withdrawing lubricant. Unused lubricant may pick up moisture or dirt. All right. So if we've got our container open, we don't close it, and we're just doing our work. It's been a week, 2 weeks, and we keep using that. Well, guess what? Moisture's going to get in there. It likes to get into the oil, and it's going to be very difficult to pull that moisture out, or even dirt for that matter of fact. So make sure you keep that oil container sealed as best you can. So adding lubricant to a system, ensure the correct amount of lubricant. Too little shortens component life, too much reduces refrigerant pumping capacity. Follow the manufacturer's recommendations. Make sure lubricant is compatible with the refrigerant. Add lubricant only if there are signs of leakage. All right, so if we find a leak on a system and some of the mineral oil is spewing out the side, does that mean we just run back up there and just throw a bunch of oil in to help the system out? No. First off, if we can fix the leak, we will. Secondly, how much oil did we just shoot out? I don't know. I don't think there is a way to know. You'd almost have to tear apart the system, pour out the oil, weigh it, pour it back in. Is it worth it? No. Our system is at a point where it's failing. I'm going to either make a repair or going to make a replacement, and I'm not going to have to worry about how much oil is in there. Okay. So, adding lubricant to a system, we already talked that. Only add if there's signs of leakage. So there's a couple of different ways. We've got this little pump. Basically, we would put this into a canister, hook up our line that goes directly to our system, and we're able to use the pump and just pump away. Oil gets sucked through the tube and gets put into the system. How much do you put in? Yet again, I don't know. Do you use a like a measuring cup or something to inject it? That may be a possibility. Same thing with these guys. Fill them up. and then just apply nitrogen or refrigerant, and it's just going to blow it into the system. Contaminated lubricant. Lubricant should be translucent. All right, that means it should be clear. If I look at it, I shouldn't see any particles or anything else in there, or it shouldn't be discolored. All right, so we've got discoloration, we've got the odor, so we may have there may be a smell to it. Could be metal shavings and chips. So we're not going to reuse any of the oil that we pulled out of an old system, hoping that one day, there may be just the perfect instance. No, we're going to use fresh oil if we can. All right. We're going to replace any contaminated lubricant, and we're going to replace the system's dryers and filters. So if we're working on a system, we want to make sure that everything is nice and clean. We're trying to refrain from dirt and moisture being in our system. All right, contaminated lubricant from a hermetic system is very dirty and smells bad. May also be acidic and can burn the skin. All right, another reason you don't want to keep that oil in a jar underneath your bed. All right, we don't want that potentially to spill and cause some issues. It may stink. Who knows what else? And that's it, gents.